Hey everyone, in this video I'm going to fill in the flow chart for quadrilaterals. So up at the top here, we're going to write down the word quadrilaterals. Then in blue, I'm always going to write down the name of the shape as we go down and become more specific. I'm going to use a pink marker to write down definitions of each of these, and then in a green marker I'm going to write down all of my properties. So, the definition of a quadrilateral, so what it means to be a quadrilateral, it's a polygon. And we know a polygon is a figure with 3 or more sides that are made of straight lines and it's closed. So it's a polygon, but this time for quadrilaterals, it has specifically 4 sides. Property of quadrilateral is that the sum of the interior angles is 360 degrees. From quadrilateral, I'm going to draw a branch. And under that branch, I'm going to write down parallelogram. This is to say that a parallelogram is a type of quadrilateral. So it is a polygon with 4 sides, and the sum of the interior angles is 360. So all of this information is true for the parallelogram. What makes a parallelogram stand out is that it has 2 pairs of opposite sides that are parallel. And that's a symbol for parallel. Some specific properties of a parallelogram. We know that the opposite sides are also congruent. We know that the opposite angles are congruent. We know that the consecutive angles are supplementary. And the last one is that the diagonals bisect each other. So those are our 4 properties for a parallelogram. Below parallelogram, I'm going to draw 2 branches. One is going to go to the rhombus, and the other one is going to go to the rectangle. And so this is to say that a rhombus is a type of parallelogram, which is a type of quadrilateral. A rectangle is a type of parallelogram, which is a type of quadrilateral. So everything up here, all of the definitions and properties for quads and parallelograms, and it's true for a rectangle. But rhombuses and rectangles, there's no line connecting them. They have properties of their own that aren't true for the other. What makes a rhombus stand out is that it has 4 congruent sides. In addition to the 4 congruent sides, we have 2 properties. One of those is that the diagonals are perpendicular, and the diagonals bisect the opposite angles. For our rectangle, what makes a rectangle stand apart from a parallelogram is that we have 4 congruent angles. All of those angles, the interior angles of a rectangle, are 90 degrees. Another property of a rectangle is that the diagonals are congruent. So again, all of this information is true for the rhombus. All of this information is true for the rectangle, but these 2 things are not true for the other. So this is not true for a rectangle. This is not true for a rhombus. This is not true for all parallelograms, and this is not true for all parallelograms. I can only work my way up. I can't work my way down. Now we're going to draw 2 branches from the rectangle and from the rhombus, and they're going to come together at the square. So a square is a type of rectangle, which is a type of parallelogram, which is a quadrilateral. A square is a type of rhombus, which is a type of parallelogram, which is a type of quadrilateral. What makes a square stand out is that we not only have 4 congruent sides, but also 4 congruent angles. So 4 congruent sides and 4 congruent angles. So all of the information, all of the definitions and properties that we have here are true for the square. Everything written down works for the square. So this is the parallelogram family. We're going to move on and draw a branch down from the quadrilateral. We have another four-sided figure that's not related to the parallelogram family. We have the trapezoid. So for the trapezoid, what makes a trapezoid stand out is that it has one pair of opposite sides that are parallel. So if I were to draw a picture of what that would look like, and again, this does not have to be isosceles, we just want the one pair of opposite sides to be parallel. A property of a trapezoid is that don't say consecutive, I'm going to say instead of consecutive leg angles, they are technically consecutive, but specifically, let's change that to leg angles. The leg angles are supplementary. So what that means is that these two angles here and these two angles here add up to 180. And that's true for all trapezoids. Because if we think about this as parallel lines, this is a parallel line, this is a parallel line. If this is my transversal, these are my same side interior angles, and those are always supplementary. To be more specific from trapezoid, we know about the isosceles trapezoid. So our isosceles trapezoid will be next. What makes an isosceles trapezoid different from a trapezoid is that we have congruent legs. So the legs are congruent. So what that would look like, we've still got those opposite parallel sides, but now these legs here are congruent. The properties of this, so not only are the leg angles supplementary, but also the base angles are congruent and the diagonals are congruent as well. So I know that this is a base angle congruent to this base angle, and this base angle is congruent to this base angle. True to also say that the leg angles here are supplementary. So if this is a leg, this is a leg, this is the base, and then this is the other base down here. All right, one more family. Another branch off of the quadrilateral. The only figure that we haven't talked about is the kite. So what makes a kite different is that we've got two pairs of consecutive sides are congruent. So in a picture, what that looks like, if I try to draw my kite here, these consecutive sides are congruent, and these consecutive sides are congruent. In my diagonal, I'm going to help out with the properties. I know that my diagonals in a kite are perpendicular. Diagonals are perpendicular. We have some angles that are congruent. So we know that the opposite angles are congruent, specifically the ones in between the legs that aren't congruent. So one tick mark, two tick marks. So I know the angle between the different tick marks is congruent to the angle in between the different tick marks. An easy way to identify that is here I have a kite cut out of paper. I know that the diagonals are congruent. I know that the diagonal one is bisected here, so this one gets bisected. If I think about these two angles and I fold my kite in half, folding the kite in half, I see that these angles overlap each other perfectly. So that's how I can really identify that, yep, those are the ones that are congruent. If I folded it in half this way, it's kind of hard to tell, but we don't have that perfect overlap. So it's only these two opposite angles that are congruent. Another thing that I notice when I fold this in half is that this diagonal is bisecting this entire angle and this entire angle down here. So if I fold this in half, I see that this angle here overlaps this angle perfectly, and the same thing with this angle and this angle. So what I'm going to write down here is that folding this in half, so say folding in half, dot, 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 you see congruent angles. So yes, we could write a property that says the pair of opposite angles are congruent and the other pair of opposite angles get bisected. That's a lot to write. When we can just identify what happens when you fold that kite in half along the diagonal, that's the bisector. So what we have here now is we have our entire quadrilateral family tree. We have a branch going off to parallelogram, a branch to trapezoid, and a branch to the kite. All of these properties are going to be extremely useful in setting up and solving for missing variables and all these other things that we're going to be able to do.